Okay, hello. I just realized that I didn't provide you with a video of how to do the second assignment. I truly apologize. You thankfully two students came in asking for assistance, and I realized that I didn't do that. My apology for that. Luckily, this isn't a very hard one to do, but we're going to go ahead and run it. Okay, so once you get into SPSS, SAS, sorry, not SPS, SAS on demand as you normally do, you want to go into your program for coding. If you didn't save the program, at the top here, you'll have this little dot icon. There's like seven little dots here, and click New SAS Program, and that'll initiate a new program. Then you can save that. But let's work with this one. One of the things I always like to do is run proc contents because sometimes I want to see what I may not remember the name of the variable. At least I can have the content ready for me. So I might run a proc contents. If you can remember how to do this, let's just go over a couple things again, just to make sure that we're all on the same page here. A PROC, and it comes up either proc or procedure. Either one's fine. Gives me, if I start typing, I'll get contents. Okay, that's good. Then you want to mention where the data are located. So data, so here equals. And in my case, I'm keeping it in a file called HSC217, and then hit dot, and then it'll come up, the data set will come up. Don't forget the semicolons at the end, and then run. So I just do the proc contents so that I can get the contents, and it'll spit that out for me. I'm not going to run it right now because I got that. Well, actually, might as well. So I run it here, little running guy, and then you have the output. If you click the arrow here, it'll give you a different window, and I like to have it in a different window so I can refer back to it. So I know we're doing BMI, physical appearance, and self-esteem. So I'm going to do depression here because these, with a t-test, you're working with a continuous variable. Okay. So it has to be a continuous variable. That's your dependent variable. Our independent variable in this case would be sex, because that's what we're using as our independent variable. So let's go back to SAS Studio and go from results to code. And here's the code for running a t-test, So it's proc t-test, data, and then wherever you store the data. So it's data is HSC217 dot, my first data set in this case. I have a variable command. So you can list all of the variables in here. And there's three that you need. So you can list them in here. The class is the variable that we're using to as an independent variable, because we want to see if there's differences in sex for those three variables. So let's start by putting in our variable names. Well, I'm doing depression. Again, you'd be doing three different variables, but you can list all three of them there. That's fine. I'm going to do depression. I know that's not one that we're using, but that's why I'm doing it. So variable is depression, and it's a continuous variable. Our class variable is sex. So that's how we're classifying, or what we're using to differentiate, or that's our independent variable, right? Okay. Highlight that and hit run. I mean, that's really easy to do, but what's more important how how we interpret the results. Okay. How we interpret the results. So here you can see the results, the depression, what the distribution looks like for females and for males, what it actually looks like versus what it should. The blue is what it should look like if it's normally distributed. We'll say that we're okay with the distribution for this exercise. I'm just trying to teach you how to do this. I mean, there might be a violation of normality. Once you get larger sample sizes, and that's a large sample size, 385, even if we divide it into male and female, that's still a large sample size for each sex. So what's going to happen is you'll probably reject the normality assumption. It's just going to happen with the larger sample sizes, but it's not, doesn't look like a horrible violation. Now, this is depression. Again, this isn't the one that you're doing. And so there are some people who have high depression, and see what they're doing is they're pulling that distribution out to the right. right? They're pulling it to the right, particularly in the females more so than the males. Okay, so let's take a look at this. What do you need to fill out for your first table? All analyses always need a descriptive statistic tables. It allows other researchers to replicate the results. That's why we do that. And here we have females and males. You have the and. So this is stuff that we did before, right? But we're going to get, I mean, what we did was we divided our sample in terms of frequencies, right? But here instead, we're looking at the mean for the females and the mean for the males. So you see the mean for females is a lot higher than for males. This is their standard deviations. And that's when you put in part of the table that asks you about just the descriptives about males and females, gives you the minimum and the maximum for each. Luckily, nobody went over 57. We see the differences. Now we're going to need the reason you have these differences. Well, the reason we have them with pooled and Satter weight is because these are related to whether or not we have equality of variance. So that's the next thing you have to do is you have to test whether we have equality of variance. Okay. Do we have equality of variance? You go to the test that says equality of variance. The null hypothesis here is that the variance is between, so each group, we compare the variance, and the null hypothesis is that the variances are equal. Sigma squared for females is equal to sigma squared for males. And again, we use the population rather than the S squared because we're generalizing to the population. Here, my p-value, so I'm looking at and this is called an F statistics, which we do with ANOVAs. The F statistic here, well, what's the probability that, that our value is greater than or equal to whatever the cutoff is for F? That's why it has a probability. Remember, the p-value is the probability of the observed value given the null hypothesis is true. Observed value or greater given the null hypothesis is true. Our F value is 1.43. And this is like if you remember, I don't know if I don't think we did ANOVA yet. I'm not 100%. I've had a really, really busy week, and sorry about that. But when you calculate the ANOVA, you need the numerator and denominator degrees of freedom to find the critical value. My p-value here is 0.0126. So if our alpha is 0.05, this value is less than that. So we consider this a significant difference and we'd reject the null. So in this case, our null was that the variances are equal. So we'll reject the null hypothesis that the variances are equal. So we cannot assume equality of variance. Okay. We go up here to our t values. So this is what we really need here. We cannot assume equality of variance. You have two different rows here. You have equal variances assumed, equal variances not assumed. And in the textbook, I use the test that does not assume equality of variance because it's more robust in situations where we don't have equal variance. And here, if we just assume equality of variance, this test doesn't do very well when we don't have equality of variance. It uses like a pooled standard deviation. So this is your, I think it's Welch's degrees of freedom, right? It's 341.56. One of the hallmarks of these degrees of freedom when you don't have equality of variance is that they're not whole numbers, right? You got 341.56, right? This is your t value and your p. So this p value here was for the equality of variance test. Once that's done, you're done. You don't need that anymore. P value here is for the t-test. So according to this, the probability of a value of 4.37 or larger, given the null hypothesis is true, is less than 0.0001. So that's definitely a result you would want to reject the null hypothesis with. All right, so, and then in terms of, I asked you for confidence intervals for the difference. You find your differences here. You see the difference is the same. A difference is a difference, right? It gives you here pooled versus, the one where it doesn't use a pooled variance. The difference is 4.9026. 1 minus 2. Sometimes it'll give you a negative value. It might be 0 minus 1. Really, I would just use a positive value because you're interested in the difference. You're not interested in how it was calculated. You just want to know what the difference is. So I would usually report it as positive. Same with the confidence intervals, right? So our confidence interval here is 2.6981 at the lower value and then 7.1071 for the upper value. Okay, so that's what I'd report. And so you do the same thing for each of the 3 variables in your assignment. Okay, these are just like basically here, these are tests of normality. So, here, if this was normal, it's quantile, the QQ plot, yeah, quantile plot, there would be perfect alignment of all the dots on this line right here, but they're not for both males and females. So there's some violation of normality, especially up at these higher levels where you see that there are outliers, right? That's what this divergence means here. And same here on the lower end, you have fewer people, so you also have this divergence from normality. Okay, that's it. Thank you very much, and I wish you all well.